Okay, so we're going to start talking about circuits. We're going to do some of the introductory stuff, build through the basics of what we need, and start climbing our way towards the more advanced things that we want to do with them. Now, as a brief heads up, so for circuits, let's see. Circuits. A little bit of background to get out of the way, just so you're used to the different terminology. There are a couple different types of circuits. Well, there are many types of circuits, but there are two main types that are usually talked about. There is DC, which is for direct current. That's where, and we're going to talk about current, what that is, but it's basically where, so for circuits, we have charged particles that are moving around, carrying energy, and trying to get stuff done. With direct current, all the charges are pretty much moving the same way, or a better description would be drifting, but we're not going to quite get into that. However, for the most part, everything's kind of going the same way the entire time. The other type is AC, for alternating current. Now, I don't want to spend too much time on this, but just kind of introducing those, so you'll hear things about AC and DC. DC is primarily related to a dead person named Thomas Edison. And AC, well, there are a lot of people kind of involved on that, but one of the big names is going to be Nikola, I hope I'm spelling that correctly, Tesla. And so the internet has its own feelings on the attributes and upsides and downsides of each of these individuals. However, I'm going to go ahead and get us beyond that by saying, however much you may think one person was good at one thing or that their ideas are the best versus someone else, we ignored most of that in the actual scientific and engineering world, and we said, hey, AC is really good at some stuff, so we're going to use it there, and DC is really good at some stuff, so we're going to use it there. In short, modern life as you know it would not be available if it weren't for us using both DC and AC. And both Edison had quite a few patents that would make him a lot of money off of DC, and Nikola Tesla had a lot of patents that would make him money off of AC. And that being said, Nikola Tesla did also apparently give some additional leeway with individuals like Westinghouse so that it demonstrated that it was not all about profit. Hang on just a second. Sorry about that. I have a cat that is looking like it's going to get up on the table, and she knows better. All right. Anyway, AC has it where it's a little more interesting, where the charges don't just drift in one direction. They actually move back and forth. Now, if you've studied some of the simple harmonic oscillator stuff or wave mechanics, it turns out that it follows a lot more like that. I'm going to save us a little bit of time here. In short, if Edison had his way and DC was all we were using, for the most part, all of us would need to live within a pretty close distance to a power generator of some kind, so a power plant. For AC, Tesla, a lot of the regular equipment that we use doesn't necessarily work very well off of AC, or would have to be heavily adapted. A lot of the simple electric motors and a number of other things, they preferentially work off of DC. DC is good for close-knit circuits, things that are relatively small or kind of in one location, and AC is really, really good at transmitting electrical energy over long distances, especially compared to DC. So in short, our power grid, sending a lot of energy long distances, is actually based off of AC. And a lot of the basic circuits that we use, most of the stuff that you encounter and that you use on a regular basis, will actually convert that over to DC so that it can use it, especially if it's got things like electric motors. Now, there are some electric motors that do work off of AC, but that being said, a lot of the smaller scale stuff goes with DC, a lot of the big stuff goes with AC. So, we use both of them. That being said, whether you're stoked about it or not, for the purposes of our course, what we're looking at is only going to be DC. At the higher levels in the engineering stuff, you might get into some of the AC, but it involves, basically, it's a lot of the same stuff that we learned here, just more complex because it'll fluctuate throughout time. All right, now that we've got that out of the way, that's a little bit of background and talking about some of the stuff that you might see in regards to circuits. I'm going to go ahead and erase this, and let's keep talking about the things that are more pertinent to what we're going to look at. Whether you're dealing with AC or DC, it turns out a lot of the same things are going to apply, though they may have to be adjusted slightly. We're going to study everything that I give you is going to be focused around DC and approximating things to be DC current. However, a lot of the things, the equations and the ideas will still apply. They might just need a small adjustment. Let's talk about the characteristics that we use, or I'm sorry, the values we use to characterize a circuit. There are 3 of them. First of which is called the electric potential difference. Now, the electric potential difference is more commonly called a voltage. That's kind of the regular term for it. However, if you're in the AP class, and in my class in general, we will preferentially use electric potential difference whenever we talk about it. On the AP Physics 1 exam, I don't think I have ever seen the word voltage, and I do not expect to see it anytime soon. Many times they'll simply call it the potential difference. Now, I may mess up and call it voltage here and there, but that's partly because I try and balance it with the real-world words that you might end up using. The more scientific side describes it by its actual name, which is a potential difference. It acts pretty much the same as a voltage. What the electric potential difference is, it is kept track of in our class and on the AP exam, last I checked, by a delta V. It is a difference in 2 different electric potentials, so one minus the other. Let's see. So the main idea behind this is you could treat this as the, wrong place for my quotation marks, driving force. Now I'm going to put quotation marks on force for circuit. It pushes the charges. Now, I put force in quotation marks because what the force is related to is actually the electric field, which is different than the electric potential. That being said, they kind of work off of one another. And so, for our purposes, whenever you're thinking about the electric potential difference, it's the thing that actually gets the charges moving. My hope is to have some more videos related to electrostatics where I start showing you the connections between force and energy. Electric potential difference is much more geared towards energy. All right, in fact, let's talk about that briefly, because we're going to talk a bit more about it in the future as well when we start introducing the more advanced stuff. How you can think about an electric potential difference is, it is exactly like a height. Now, to introduce that, let me actually bring in one other thing, our units. The units, the SI unit for electric potential difference, is the volt, capital V, named after Alessandro Volta, one of the early scientists. In fact, he was one of the first ones credited with making what we now call a battery. In fact, in some old-fashioned books, you might even see it referred to as something called a voltaic pile, which is what he originally developed. That's what they called it. The idea behind this is the following. So let's compare this to gravity, which is something that we're a lot more familiar with. Turns out gravity and electricity, the electric force, I should say, are somewhat similar, and that's kind of implied by the universal gravitational constant, or equation, which is G, mass 1, mass 2, divided by the distance between them squared. Well, we've learned that Coulomb's law predicts the electric force, which is Coulomb's constant, times charge 1 times charge 2, divided by the distance between them squared. Their equations are very similar, and they actually act in many ways very similarly. They have potential energies associated with them too. So, for instance, with gravity, I've got, bad markers. I've got 2 objects, and I lift them up by a certain amount. They're at a height of maybe 10 centimeters or so. They have some gravitational potential energy. If I let go of them, that can be converted into another form of energy, namely kinetic energy, and then sound and thermal energy from a collision. It's energy moving from one place to another. Now, these 2 are both the same mass. I could bring one of them up about 5 centimeters and then the other one up maybe about 10 centimeters or so, and I could see that this one is going to have more gravitational potential energy because they're at different heights and they have the same mass. Now I can do the following, though, where I can take this one comes up 5, and this one comes up 10. I actually don't know which one has more energy because this one has more mass. So when it comes to the energy, some of it is based off of how high the thing is, and for gravity, how strong gravity is, say here near the surface of the Earth. But part of what goes into the energy is the property of that object. The more massive the object, the more gravitational potential energy. In fact, I could actually write this out a little bit, where with the gravitational potential energy, we would have something like mgh, where we have the strength of the gravitational field, how strong gravity is there basically, the mass of the object, and how high it is. Now, the electric potential is basically these two things together. It's the strength of the field, the electric field, and effectively how high up these objects are. In fact, I'm going to compare electric potential differences to different heights. So I could then say that this one is a charge at, I keep doing that, maybe this one's at 5 volts and this one's at 10 volts. They're different heights. Now the thing about volts are, they're completely independent of the property of the object itself, which in this case would be the charge. It's like saying, I'm not going to tell you what's at the heights. We've got two different objects. We can compare their relative energies. The one higher up has more energy, all things being equal. But we don't know how much energy it totally has unless we know the masses of those objects. In other words, what objects we put there. Now, this is something that I'll point out a little bit as we go through circuits. The reason that we have kind of this complex idea is because we're going to end up with different amounts of charge going through our circuit under different conditions. And so having things that are independent of what object you're talking about, G and H, for instance, not including M, allows us to be a lot more versatile in what we do. All right. So that's a little bit about this. In short, you're going to hear me refer to potential differences as being very much like heights. And as a result, you could look at it where it's not actually the height that makes things move, it's the force of gravity. But when you have stuff up at higher heights, they will have more energy associated with them. Things have a tendency of rolling downhill or sliding downhill under the right circumstances. The same thing applies for our electric potential. It is actually related to energy, but it serves to actually, as you could imagine it, as what's pushing the charges through our circuit. One final thing I'm going to bring up. A volt, the SI unit of a volt, is equal to a joule per coulomb. That's energy divided by charge. So we don't know how much energy it has until we know what charge is put there. All right, great. That's a bit about on electric potential difference. It's one of the main things that we will be keeping track of for our circuits. Let's take a look at our next characteristic. All right, our next characteristic is going to be current. My red marker is not the best ever. I apologize. Current. All right, current is sometimes called amperage, but that's actually a bigger word than current, so I pretty much won't use it again. I'd recommend getting used to the word current. It's still very commonly used. Amperage is sometimes thrown out there, but not quite the same. Anyway, current is what we're going to be working with. Its variable is a capital I. Now, not to be confused with an impulse, which is a capital J with a vector sign, or a moment of inertia, which is also a capital I. So please keep track of the context that you're using these in. Unfortunately, there are only so many letters in the alphabet. Current, I. Current is the flow of charges past a given point in a given time. Okay. Now, this is one thing that I'm going to draw your attention back to. At first, it's going to be easy to forget, but when we get to the more advanced part of this, it helps to know that current describes how many charges are going past a given point, one spot in your circuit. When we first start out, we're going to have basically only one path in the circuit, so our total current is also going to be the current at any of the individual points. But we'll take a look at that as we develop it further. The big example that I like to give on this is, imagine you're looking out the window onto the street. some bad curtains. But we're watching the street. And we watch some cars go by. Imagine that it's the street right in front of school. So if we're watching at maybe 8 a.m., we would get something like, it's a pretty busy street actually, especially at 8 a.m. So we might get something like maybe 50 cars every 1 minute. So there's a time period that we're watching and we're counting how many cars go driving by. Now that's going to be a little bit different than if we say looked at 2 a.m. 2 a.m. we might get 1 car per minute, or maybe 2 cars per minute. That's on this relatively busy street. If we were to look at, say, 2:30 p.m., when school lets out, we would get a whole bunch of cars, maybe 100 cars per minute. Or, depending on how you look at it, all the cars might be brought to a stop, traffic jam there, and you might end up with very few cars. You might see 0 cars go by every minute because you have to watch for 5 minutes just to see 1 car start moving. It can all depend. The biggest thing that I want to bring up is this. Now, this is also when we're looking out the window at the high school. If you go down this road another couple miles out into where there's fewer businesses, fewer residences, that sort of thing, and you were to watch the road there, even at 8 a.m., you might only get 2 cars per minute. And at 2 a.m., you might only get 1/10 of a car per minute. In other words, you only see 1 car every 10 minutes, or even worse. So one thing to keep in mind is the point, a given point. So when we get to more advanced parts of the circuit, you've got to keep in mind that the current is only at the specific point that you're looking at. All right. Now, bringing it back together with what we want to take a look at, our current talks about charges moving through the circuit. And these charges are the ones that are effectively moving downhill, and they take energy and they move it through the circuit. The units for current are the ampere, better known as the amp. In fact, I'll probably just call them amps. They're abbreviated with a capital A. And an amp, ampere technically, is equal to Coulomb divided by second. It's charge divided by time. Instead of cars, we're counting how many charges go by. And so if you're looking at 1 point and 1 Coulomb goes by every second, then you have 1 amp, an ampere. Okay, so this is charge per unit time. All right, so these are 2 of the characteristics. I'm going to double check that everything's recording fine. We're going to pick up in just a moment. Okay, so we just finished talking about the current. Let's go on to our third characteristic that we use, or I'm sorry, not characteristic, our third value that we use to characterize simple resistor circuits. All right. We get to our last one. Resistance. It's kept track of as a capital R. And what this does is it describes how hard it is for current or charges to move through a resistor. Now we're going to start off looking only at resistor-based circuits. Now resistors are very important in circuits, and even in the most complex circuits, you'll probably be dealing with resistors showing up in there. We're going to deal with this more as we start working through it, but in short, there are the 3 things working together. You have your potential difference, your voltage, that gives you an idea of how much oomph there is in the circuit, basically how hard it can push charges. And then you have the amount of charges that actually get moving, and that's being balanced out by the resistance. More resistance means it's harder for the charges to move, and you end up with fewer of them moving through the circuit. Lower resistance for a given potential difference will result in a higher current, more charges moving because it becomes easier for them to move through. Now we're going to develop this further, but the big thing that we need to introduce right now to finish this out is is going to be the units. The SI unit for resistance is called the ohm. It is abbreviated with an uppercase, a capital, Greek omega. It looks kind of like a horseshoe. Now, for a full breakdown on this, there are other ways that we can write it. I'm not going to go through all the details, but we can write that an ohm is equal to... Oh, I forgot to bring my papers here. Give me just a second. That would be a joule times second divided by Coulomb squared. I'm pretty certain that's right. I'll double check and add a disclaimer if I've got that wrong. But I'm pretty certain that's what you end up with. Yeah, that should be it. Joule times second divided by Coulomb squared is what an ohm is made up of. All right. So now we've got our resistance. There are a few other things that I do want to talk about. A little bit of terminology because you're going to see it when we start working with the actual equipment. And then I'm going to introduce some circuit diagrams so that we can actually represent these in drawings. First and foremost, I'm going to erase resistance. We're hopefully going to get a better feel for what's going on with resistance as we start using it. The next video will feature us developing or collecting some data so that we can actually get an idea of what's going on with resistance. So let's see. First and foremost, let's talk about a couple different, or a little bit of terminology in our circuits. Open circuit. I'm going to mark that this means off. This is the regular setting for a circuit to be off. Oh, actually, let's introduce a little bit about that. I apologize. There's one other thing that we should probably look at. Let's go with components. A little bit of terminology. Components. A small part of a circuit. Small part of a circuit to do a job. So examples of this, let me give you some examples. So when I say components, it basically means the little parts of a circuit that make up a total circuit. So examples of this would be a battery, that's a component. A switch, that's a component. The battery's job is to supply energy. The switch's job is to allow you to control where that energy goes, or if it's going at all. We have wires. Their job is to let charges and energy flow from one component to another. We've got resistors. Their job is to control how much energy is being let out of the battery at a given time so that we get the appropriate amount of energy to where it needs to go. Now, these are the main ones that we're actually going to be dealing with. Other examples include things like capacitors. Those are small components that allow you to store some extra charge and energy for different uses. A lot of times they're similar to batteries, but they can actually release a lot of energy all at once. There are inductors, which are another form of energy storage and ways that you can control how quickly current flows through a circuit. So in the APC classes, we'll be talking about capacitors and inductors, but in all the other classes, we'll be introducing everything that we need, basically with batteries, switches, wires, and resistors. They all have different jobs that they do. There are additional things too. There's all sorts of stuff like diodes and LEDs and bulbs and a bunch of other things. But components are the small parts of the circuit that you basically string together, each of them doing their part to make the whole thing work. And a circuit, which we've been talking about, is a closed loop of components to achieve a task, achieve a goal, for instance. Now, usually that goal is converting electrical energy into another form. So a good example of that would be lights, light bulbs. You get them wired up, a light bulb by itself. In fact, let's bring some of these in. I've got a light bulb here. It by itself does nothing. So the component is a useful thing, but it can't do anything by itself. So we bring in a set of batteries here, and we have some wires that connect them. And here's our light bulb, and I put these together, and they achieve a task. to convert electrical energy into light energy. Now that's one of the things that allows us to work late into the evening, among other things. Electric lights are kind of an important part of modern society. That's just one example. You also have things like televisions, you have speakers, you have all sorts of things. So, the goal of a circuit is basically converting electrical energy into another form that's useful for us somehow. And we need a closed loop because that's the only way that we can get the charges to move around the way they do. All right. Now that we've got those, I'll introduce the next part here. I'm going to erase this. Let's keep going. Now we'll get to open circuit. I apologize about that. This might be better characterized as off. And the thing about the closed or the open circuit is it's a closed loop, but broken at one point, or sometimes several points, but one point is usually all you need. Broken at one point. No charges, and therefore no energy can flow. Now, normally with these open circuits, you do that on purpose. So a good example is, yoink, here are some of my snap circuit kits. Let me show you a good example of an open circuit. Give me just a moment while I rework some of this. So I'm going to make a simple circuit with a light bulb and then a battery. So we've got a battery here, we've got a light bulb here, and I've got a switch that I'm going to put in place here. Now, I don't think I brought any threes or got any threes out, at least not right away. Do I have any threes easy to grab? There's one. Great. Okay, so here's my circuit. It achieves the goal of converting electrical energy into light energy. I'm going to flip the switch on. Everything's good. Our circuit's working fine. We're going to get to what this is called in just a moment. Heads up, spoiler alert, it's called a closed circuit because I have closed the switch, putting them together, everything is connected, charges are moving around. This, the off position, I've now broken the switch. There is not a complete loop because I've broken it at one point. No charges are leaving the battery. They're not going anywhere, and no energy is leaving the battery. So this is a good offsetting. It is also called an open circuit. All right. The next one is called a closed circuit. Now, there's also closed circuit television and other stuff. That means something slightly different. But for our purposes, a closed circuit is just when you've got it set to on. I'm going to close the switch. We have a completely closed loop. Let's see, a closed loop. A closed loop where charges and energy flow where intended. Okay, now we're going to talk about that a little bit more, but this is doing exactly what I want it to do. Energy, charges are leaving the battery, going through the circuit here, a huge roundabout, and as these charges go through the circuit, they release energy, and that energy can be turned into other forms that we want, like this light energy here. That's what this circuit is designed for, and everything is going exactly the way I intended. All right, now we're going to switch this out just a little bit to see our last one. This is the main reason that I'm walking you through these, because I'm going to use this terminology, and I want you to understand what I'm saying if and when I say it. The last one is called a short circuit. Now, a lot of people use this phrase, but they think it just means that something's acting weird or just not working. In fact, many times people think that an open circuit is a short circuit, but they're not, in fact, the same thing. Short circuit. This one is a closed loop where charges and energy flow somewhere unwanted or not intended. Now, these can be dangerous. The equipment we're going to be working with is actually pretty well rated, so that's one of the reasons why I like these. So for instance, this is a closed circuit. This is an open circuit. I can break the connection. This, what I'm about to show you, is something that a lot of students end up with, and they don't realize it. They think everything's working fine. It's just a little weird, but this is a short circuit. What I've done here is right now my switch is off and the light bulb is on, and when I flip the switch on, the light bulb goes off. This is a short circuit. Here's the problem. The light bulb is off, so it does not seem any different than this. This is an open circuit. The thing about this is we do not have a closed loop, so charges from the battery, charges in the circuit, cannot move at all. No charges move, and no energy is leaving the battery. This is a closed circuit. Charges are leaving the battery, they're taking the energy where intended. In this case, when I have this broken, there is no path between these, and so all of the charges are moving through the light bulb. Now we're going to learn about this because charges are going to divvy themselves up based on how easy it is to go through something. It's hard to go through a light bulb. This switch is designed to be really easy to go through. So right now, nothing's going through it because the switch is open. It's switched to off. Now I'm going to close the switch that connects these. So we have charges leaving the battery. They're just going through here, taking a shortcut, hence a short circuit. The problem with this is charges are leaving the battery and they're taking energy with them. And that energy is no longer going somewhere useful, like going into the light bulb, which means it's got to go somewhere else. Energy doesn't just evaporate, it must go somewhere else. If I leave this connected the way that it is, these batteries are going to get hotter and hotter because the energy has to go somewhere, so it will become thermal energy. This is a bad thing. And in fact, if we weren't using some of this equipment, that could be very dangerous because if the batteries get hot enough, they'll end up rupturing and you might end up with battery acid somewhere. So keep an eye out for short circuits. When we're working with this equipment, unless you have a good reason, nothing should go from this over to the opposite end. The only exception to that is a light bulb. Light bulbs will not be shorting it. Okay? I'll show you here. We actually get both of the lights coming on. All right. I'm going to check the camera once more, and then we'll finish up with some diagrams and be done with this video. All right, so finishing up. We just finished talking about some of the terminology. Open circuit, closed circuit, short circuit. And both I and the AP exam will refer to switches as being open or closed. When they're open, that means nothing goes through them. When they're closed, that means, charges can go through them. They act exactly like a wire. So that's a little bit of useful terminology for us to know. All right. Let's go through and learn a little bit of circuit diagrams. These are things you're going to be seeing both in my class and in real life and on the AP exam. So first and foremost, we've got, for circuit diagrams, let's go with a battery or a voltage supply. So what the battery is, the drawing looks like this. One long line, one short line, one long line, one short line. Sometimes this is it drawn upright. You could also do one on the side. Short line, long line, short line, long line. I will always draw them with the 4 lines. That's my preference. It is not uncommon to see them with one short line and one long line. I don't like those because that looks a lot more like capacitors, which we'll see here in a little while. Sometimes you will also see them with a whole bunch of lines. Usually that's to denote that you've got something that's high voltage. That being said, the combination of a short line and a long line in this setup is basically how you draw a battery. Now, as a quick heads up on this, the long line and the short line are kind of useful because they denote the following. The long line is always the positive side of the battery, and the short line is always the negative. Now, when we deal with current, I forgot to mention this before, but we will be treating it as positive charges moving through a circuit. In reality, it's actually negative charges moving the opposite way, but it turns out they'll still give us the correct answers. There are some strange reasons why we keep doing it. It traces back to basically people who first set this up. They had a 50-50 chance. They guessed that it was positive charges moving, and then later, like 100 years later, we figured out that it's actually the opposite, and by that time we had too much stuff built up off of it. That being said, most places, with only a handful of exceptions that I'm aware of, when they're working with circuitry type stuff, they'll always treat it as positive charges moving one way instead of negative charges moving the other. So just be aware of that. we will continue to do that through class. This is how you draw a battery. All right, next one. Let's go with a switch. Oh, real quick, with some of our lab equipment, I'll go ahead and point this out. Another reason why I like these, you'll see that we end up with that exact symbol right here. Long line, short line, long line, short line. And they've got this side marked as positive and this side marked as negative. So I like these circuit kits because they do actually show the diagrams, as we'll see for each one. For a switch, it looks a lot like this. Usually a circle, a line like this, and another circle. Sometimes they'll put these lines here where it fits into some wires. And so what this is supposed to represent is a physical thing like what we did in class with the paper clips, where when it's like this, they're not actually touching and there's no complete circuit. And then you close the switch by bringing this in. You can imagine that this ticks down in place, completing one straight line or wire. Now, drawn on its side, it might look like this. I'll say the following: I get really lazy and I don't always draw switches into my circuits, but it's always nice being able to control on or off. So if you don't see them there, feel free to assume that they're there. For our purposes, especially in the AP classes, later on we will be drawing them in because we're going to talk about how flipping the switches, either opening or closing them, can and will change a circuit and being able to predict those things. Next thing, a wire. Wires are actually pretty easy. They're just a straight line. It might be down like this. They can go around corners. They can go off at jaunty angles. You can even do them as squiggly lines, although we usually try and keep our circuit diagrams looking a little bit nicer, so we'll do them as straight lines. Now, it's a little redundant to say, but once again, we've got kind of a straight line on this. These are supposed to be our wires for our snap circuit kits. In this case, it has a number for how many units long it is. All right, and finally, well, not quite finally, but the main other one that we're going to use is a resistor, and it looks like this. It's jaggedy lines like this. Let's see, here's a resistor. You can actually see the same diagram here. The physical resistor is on top of it, but you can see the diagram there. Now this can also be drawn on its side very poorly. I'll be completely honest, as we go on, I will eventually just be doing them as squiggles like this, because I'm going to get lazy. I'll try and draw them out as best I can like this until we get used to them. They're the main thing that we're going to be working with, especially at the beginning. Other ones to bring up. A light bulb. Now we're going to pretend that light bulbs and resistors are kind of interchangeable, even though technically they're not. We'll see that in the next video. But the standard drawing for a light bulb is usually something like this. This represents the filament, and then you have a bulb around it. Some other ones to take a look at are capacitors. Capacitors look like this. They are two same length lines. Like I said, they look kind of like the battery one. So up and down, they'd look like this. And then other ones that we might take a look at, depending on which class you're in, are things like inductors. Those are magnetic circuit components. They're swoopy lines, little loops, not sharp edges like the resistor. Now, there's a whole bunch of other diagrams, but this will get you through pretty much everything that we'll be using for the classes that we're in. Okay? So, that's our grand overview on circuits.